In this video, we'll introduce the concept of free energy in a restricted Boltzmann machine. So we've seen that a restricted Boltzmann machine defines a distribution over the inputs and a latent vector of binary hidden units. Now in this video, we'll look at what the actual marginal distribution over X only, so over our inputs that we're interested in modeling, looks like, to try to gain some intuition as to how a restricted Boltzmann machine can make certain types of values for the input vector more likely and other vectors less likely. So in other words, how it can actually model a distribution over binary vectors. So what does P of X look like? So P of X, if we wanted to write it down, well, we can write it down as just the sum over all potential binary vectors, so binary patterns we could get at the hidden layer, of the probability of observing that hidden layer with the given value of X. And now we can just write down what P of X and H is, just the exponential of the negative energy divided by the partition function. And what we can show is that this sum over an exponential number of binary vectors, the exponential number of patterns in the hidden layer, can actually be written down in a more efficient expression, more efficient to compute. So we can write it down as the exponential of a bias term that involves only X and its biases, plus a sum over all hidden layers of the logarithm of 1 plus the exponential of a linear transform of the input, and looking at the linear transform for each hidden unit. So in other words, we can actually write it down as a linear term plus, so the exponential of a linear term plus a sum over all hidden units of a non-linearly transformed version of the linear transformation associated with each hidden unit. And if you look at the literature on restricted Boltzmann machine, if you see mentioned the notion of free energy, well, we're just referring to minus this, so the negative of this whole term here. So that would be the free energy in a restricted Boltzmann machine. So let's first actually do this derivation here, how we go from that to this. And notice again that this might be a surprising result because we've transformed a summation over an exponential number of terms into an expression that requires a sum over a linear number of terms, linear in the number of hidden units. Okay, so P of X is the marginalization of the joint distribution by summing over all values of H. And so that here, this is just P of X and H. Now, let's actually notice that the exponential of that does not depend on the hidden layer. So we can actually put it in front of the sum. So it goes here. I'm writing explicitly that this sum over all binary vectors is, we can write it down as a series of nested sums over H1 up to H capital H. And then I'm writing down this term here and this term here, similarly like we've done in the demonstration for the conditional distribution. I'm writing it as a sum over all hidden unit indices of a term that involves only a single hidden unit, Hj. Then I'm using the same step that I've used in the derivation of the conditional distribution, that essentially this is the exponential of a sum, so that's the product of the exponentiated values for these terms here. And so in this product of terms, each factor only depends on one hidden unit, which means that this nested sums can now become a product of individual sums over each individual hidden unit here. And now, because this sum is over just two terms, so a term where the hidden unit is equal to 0 and another one where it's equal to 1, then I can just write this down explicitly. So when h1 is equal to 0, then this is the exponential of 0, which is 1. And when it's equal to 1, then it's just the exponential of b1 plus the product of x with the first row of w. And then I get a similar expression for all hidden units until the last hidden unit. So the hidden unit capital H. Then I'll also write this term here as an exponential, the exponential of a term. So I'm just going to add the exponential of the log of the term that I have here. I'll do that for this one too. So I have the exponential of the log of the original term. This allows me to write the product of all of these exponentials here as a single exponential where I'm summing the terms inside the exponentials. So I'm summing the biased term, and then I'm summing all of the logs of 1 plus the exponential of the linear transformations of x for each hidden unit, which I'm finding now here. So we finished our demonstration that p of x can be written down like this. So it's just the exponential of a sum of a bunch of terms, and there's only capital H number of such terms. Now in this form, what's nice is that we'll be able to get a little bit of intuition for how we can adjust the parameters here to make the probability for a given input vector x to increase. So how can we change it so that we increase the probability of a given input vector x? First, I actually introduce a notation for the nonlinearity log of 1 plus x. It's known as the soft plus function, which we're seeing in this plot here. So first consider the dotted line, which is just the maximum between 0 and the input, which I'll just call x. So assume that this axis is x. So we see that indeed it's linear if the input of the nonlinearity, the argument, is greater than 0, and otherwise it's clamped at 0. Now soft plus, you can think of it as a smooth version of that function. So we see that as the argument becomes greater and greater and greater, then it becomes closer and closer and closer to a linear function. And if it's actually quite negative, then it's going to be lower bounded by 0, and as we go towards minus the infinity, we are getting closer and closer to 0. Okay, so it's kind of a subversion of this function here, sometimes known as the it actually corresponds to the rectified linear function that we've seen when we've described activation functions for neural networks. Okay, so now what does it take? What can we do to make p of x big? Well, we need that term to be big. So if the input vector x is well aligned with the bias vector c, that is, if the elements of x are positive when r1 when the terms of the associated terms in the c vector are positive, and 0 when they're negative, then this can become great. This can become big. Now we also need these terms to become big. So we notice that here this only looks at individual values of x. So we can't really model dependencies between pairs of inputs, or even just the joint configuration of the elements in the input vector. So this term here is now going to model dependencies between the elements in the input vector. So for that to become big, then we want the input vector to be well aligned with the rows of W. So for a given hidden unit J, if the dot product between the jth row and the vector x is big, then this term is going to become big. So for a given hidden unit, if x is positive for the inputs to which the jth hidden layer is positively connected, and if it's 0 for the other input neurons to which it's negatively connected, then this has a chance of being bigger. And then we have the bias of the hidden unit, which essentially controls how big this needs to be for the soft plus to be much bigger than 0. So another way of saying this is that we can think of each hidden unit as acting as a feature where we look at whether a feature is present in the input x by multiplying by its associated weight so its associated row in the matrix W. And then the bias just determines what it means for a feature to actually be present. So how big must this term be for us to consider that indeed this particular pattern associated with that feature is meaningfully present in the input. So for instance, imagine that Bj is quite negative. Like for instance, imagine that it's -4, that it means that once I've computed that, then the soft plus is actually quite close to 0. And so it means that if I wanted the soft plus to be non-zero and actually increase the probability for the observation x, then I need to fight the contribution from the bias and be actually much greater than 0 than, say, if the bias had been 0 and I had started my activation, computing my activation here. And so that's the role that each different parameters are playing. And now it makes it more explicit that really the hidden units, we can really think of them as features. And so if we want the probability of all of our training examples to be high, then we want the different rows of W to be well aligned and represent meaningful features that are present, that are often present in all of our training data sets. And so the more these terms are going to be positive, then the greater the probability associated with a given input is going to be. And so training will correspond to finding these rows of W along with their corresponding biases, which are such that this term tends to be quite high for the inputs that we have in our training set. So we'll want these rows to essentially look at different specific features of inputs that we tend to see for in our training set. All right, so so we've introduced the notion of a free energy, which is involved in computing P of x. We can't compute P of x tractably in the general case because, again, of the partition function. However, introducing the free energy has allowed us to get an expression where it becomes more obvious what an RBM needs to do to make certain inputs, values of input vectors have high probability. And so in this case, if we were to train it on a training set, what it needs to do to make the training set more likely.